Okay, let's continue talking about areas. One thing I want to make sure everyone understands, the difference between R sub n and A, the area under a curve. R sub n is just the sum of the areas of the rectangles, right? You could think of it as an approximation to the area under the curve, but it's not the same thing as the area under the curve. Technically, this is the sum of all of the areas of the rectangles where you use the right endpoint of each subinterval to compute the height of the rectangle, right? Then the area is the limit as n goes to infinity of R sub n. You could say the more rectangles you use, the closer R sub n is to A, but technically A is the limit as n goes to infinity of R sub n. Don't get them confused. Okay, let's get started. Let's look at this example. Back to approximating areas under curves. The function's square root of x, and we want to approximate the area from 0 to 4 using 4 rectangles. And we're going to use what are called the upper sums. The upper sums mean on each subinterval, let's see, b minus a over n would be 4 minus 0 over 4, which is 1. So on each subinterval, to get the upper sum, we're going to use whichever x value gives you the biggest height. Okay. Since this function is increasing, wouldn't the upper sums, to get that, wouldn't we use the right endpoint on this example? So anyway, in that case, x sub 1 would be 1, x sub 2 would be 2, and so on. So r sub 4 would be f of x sub 1 delta x plus f of x sub 2 delta x, and so on. So when you compute that, f of x1 would be the square root of 1 times delta x, which is 1. The area of the second rectangle would be f of x sub 2, which would be square root of 2 times 1, and so on. You get 6.14. Now let's do the same thing, only this time this time we're going to use the what are called the lower sums. Now when you approximate the area with lower sums, on each n equals 4, on each subinterval you use whichever x value gives you the smallest f of x, or the smallest height. So again, since the function is increasing, to get the lower sums, you'd use the left endpoint of each subinterval when you compute the height, right? Anyway, so that turns out to be L sub 4. The first rectangle has area 0, because you're using 0 for your x sub 1. For the second rectangle, you'd use the left endpoint, so it becomes the square root of 1 times 1, and so on. You get 4.14 approximately for the lower sums. We could even use the midpoints. Same thing, we're going to have n equal 4 and use the midpoints. Doesn't it seem like the midpoints would be more accurate? Let's look at this first rectangle. The reason why I say that is because you see this is an over estimate here. This is going to be an error, an over error, and this is going to be an under error here. So they almost like counterbalance each other. So it seems like, I'm not saying it's exactly the same, but it should be closer than the other two. There's less error. Anyway, so what you do is, in each subinterval, you use the midpoint, plug that into the function to compute the height of the rectangle. So if you use the midpoints of each subinterval, you get 0.5, 1.5, 2.5, and 3.5. Plug them into the function. So the first rectangle is going to have area square root of 0.5 times 1. Second rectangle is going to have area square root of 1.5 times 1, and so on. You end up with 5.3. Let's find an expression now for the exact area under the curve of f of x equals square root of x. Now when it says the exact area under the curve, that's a. That's going to be the limit as n goes to infinity of r sub n, right? So we're going to have to compute r sub n. So if you have n rectangles, delta x becomes b minus a over n, so it becomes 4 minus 0 over n. So 4 over n is the width of each rectangle. Now, if you use the right endpoint of each subinterval, the first subinterval you're going to use the right endpoint. So you're going to use 4 over n for the first x sub 1, and then x sub 2 you're going to use the right endpoint of the next subinterval. So you're going to add delta x onto that and get 8 over n for the second one. If you keep on going, what you're going to end up with is the ith interval, the typical ith interval. If you think about it, it's going to be 4i over n. That'll give you the right endpoint of the ith interval. And then the last interval would be 4, wouldn't it? The right endpoint of the last interval would be 4. That's really important because when you compute r sub n, you have to compute this. You have to compute f of x sub I. So what is f of x sub I? Isn't it the square root of 4i over n times delta x times 4 over n? This is an expression for r sub n. So you end up with, you can simplify that a bit, I guess, because you could, square root of 4 is 2, so you get 8, and you have the square root of I, you have the square root of n on the bottom. So an expression for a, we're not actually going to compute it, we're just going to write the expression, is the limit as n goes to infinity of this. And we can actually pull the 8 out of the summation, and same with the n times square root of n. So let's just leave it like this. This is good enough. Let's do another one. Find an expression for the exact area under f of x equals e to the x on 0 to 2. Okay, so again, we're going to have to find r sub n by looking at, we have to compute delta x first of all. Delta x is 2 minus 0 over n, so that there's delta x. Now when you compute r sub n, I think the hardest part might be to find out what x sub I is. That's the right endpoint of the ith subinterval. Just count it out. X sub 1 would be the right endpoint of the first subinterval, so you start at 0, the right endpoint would be 2 over n. X sub 2 would be, you'd march over another delta x, so the right endpoint would be 4 over n, and so on. So x sub I turns out to be 2i over n. So what would r sub n be? R sub n is the summation I equals 1 to n of f of x sub I delta x. So you end up with, when you plug that into the function, what is the function e to the x? So it's e to the 2i over n times delta x. This is not the area, this is the sum of the areas of the rectangles. The area would be the limit as n goes to infinity of this. And what you could do is pull the 2 over n out of the summation. Suppose I give you the area, an expression that gives you the area of a region. You've got to tell me what the function is and what the interval is for x. In other words, tell me what the region is. It's kind of tricky unless you know what to look for. If you look at what we just did, your delta x is probably right there. Your delta, if you think of it in terms of this definition, part of it is your delta x and part of it is your f of x sub I. So this is going to be your f of x sub I, this is your delta x. So if you work backwards then, delta x is b minus a over n, so that's 3 over n. So let's see if this works. Try a equals 0, b equals 3. That might work. In that case, this is important right here. If a is 0, then your x sub I will always be a plus I delta x. That really is important to remember. So in other words, your x sub I looks like from the formula is going to be 3i over n. So it looks like, so then what would the function be? If this is f of x sub I, the function would have to be the square root of x minus 5, and the interval is from 0 to 3. Pretty sneaky, huh? See if you can do this one. This is easier, I think. This is probably your delta x right here, and this is probably your x sub I right there. So your delta x is always b minus a over n, so that would be pi over 2n. A is oftentimes 0. Try that first and see if that works. If a is 0, then b would be pi over 2, wouldn't it? So then x sub I is a plus I delta x, since a is 0. Your I delta x becomes pi I over 2n. So this is just x sub I right here. So what is the function? The function would be sine x. Once you think you have it, see if you can read it back and see if it makes sense. Last thing I want to talk about is, this is a good example because sometimes we're not always talking about areas. Here's a table that gives you the time and the velocity. And we're going to use the fact that distance equals rate times time. So if you have actually 3 time periods, 0 to 5, 5 to 10, and 10 to 15, we're going to approximate the distance traveled by multiplying the length of the interval by the velocity. One thing that's kind of important though, very sneaky, we're going to first of all have to convert minutes to hours. So 5-minute interval would be 1/12 hour. If you want to look at an upper sum, what you would do is you'd use the highest value of the velocity in each time interval. So from 0 to 5, let's use 30. Here from 5 to 10, you'd use 25. And from 10 to 15, you'd use 30. So you get an upper estimate. The total distance traveled would be 7.1 miles. If you use a lower estimate for the distance traveled, you would use the smaller value in each of the time intervals. So from 0 to 5, you'd use 20. And from 5 to 10, you'd use 20. And from 10 to 15, you use 25. You end up with 5.4 miles. Alrighty, we gotta go. Bye-bye.